And there are a lot of candidates who do put their stuff in. So basically, this will give you your local election ballot that you will actually get at the voter polls by your address, because it's all about where you live and what precinct you live in. So you put in your address. Does anybody remember the address of the school? Yeah, I got it right here.
422 West Jeff.
Yes, so let me put that in. 422 West Jefferson Street. Palmer is the city. Texas is the state. What's the zip code?
75152.
152, thank you. I live in a different zip code. So we'll just use the school's website. And on the left it says find out what's on your ballot. You click explore now. And it will tell you, well, you gotta click your language. It will tell you everything that you can vote for. And so note that, yeah, we've got presidential elections going on this go round. But there's a lot more to go than just that. John Cornyn's running for re-election against Mary J. Hagar, the Democratic candidate. And if you don't like either one of those, you got a Libertarian and a Green Party guy to kind of throw into the mix if you just want to do like a protest vote. Texas Railroad Commissioner sounds kind of outdated, but they actually control quite a bit of stuff, including roads and oil and gas. We're voting on a bunch of Texas Supreme Court justices, which is interesting because there's a big fight over the national Supreme Court justice who's getting appointed. But on the state level, you actually get to vote directly for what justices get appointed to the Texas Supreme Court. And I assume that it's not a lifetime appointment since there's so many going on. Yeah, because Hesh is running for re-election. And so, you know, these people have to run for election every so often and they don't get just a lifetime appointment to it. Texas State Board of Education, Texas State Representative. So this would be someone that represents our district in Austin for the Texas government. Some more judges down here at the bottom. Texas U.S. Representative, District 6. So this would be who represents us in the House of Representatives in Washington. And then Texas State Senator, District 22. I don't know enough about Texas. I've taken a Texas government class, but my wife asked me the other day, and I was like, I don't remember how many senators versus Congress people we have in the state government. Because I know the national government is 100 senators, like 530 something Congress people, but I don't know about the Texas one. But just as an example, let's pick one of these. Let's pick one of the higher up ones so you can kind of see. So if you didn't know anything about U.S. Senator, you click on this, you go down, and unless you're planning on making a protest vote for the Libertarian or the Green Party, it's really between the Democrat and the Republican. And you can pull this up, and this is actually a good one. Both of them have gotten on this website and answered questions. So they give you their basic statement, what training, experience, background qualify you for this position. You can click on their websites or Facebook pages to get more information. And then they literally ask like very specific questions. They have a question on immigration. What are your priorities regarding immigration? Healthcare. How would you address healthcare access and the cost of healthcare? And what? And then your internet crashes, and so I'm not going to bother pulling it back up. But that is a pretty good website to start at. Let's see, is it going to give me right back to it? Yeah, not bad, not bad. And so that is a pretty good website to start with. You can actually go down, and once you get your choices, I forget exactly how they do this. Oh, you can click select this candidate and literally go down every step. And at the end, you can print off a list of all the people that you've selected, take it with you into the poll. And that way you don't have to remember people's names or what you're doing. And you can actually vote for however you want to vote, which I think is a much more informed way than just going in and voting straight party ticket for whoever you want. Because A, it's easy to vote straight party ticket during this, but if you're voting in the primaries, which are sometimes more important, especially in Texas, because a lot of positions go unopposed from Republican standpoint. There's no Democrats. Voting in the primary is actually voting who's going to win, because most Republicans are going to win. So you can't vote just straight party ticket in a primary. Everybody's a Republican or everybody's a Democrat, depending on which one you get. So this is a good website to start off with. It's a national website, and a lot of people use it and go to it. So I would recommend this if you're going to vote, because don't forget, there's more than just that top line. You don't have to fill all of them out. You can just go in and vote just for president, or if you hate the presidential candidates, you can go in and vote for everybody but president. But if you want to actually vote and understand some of the things that the people stand for, this website is kind of like a central hub to get it directly from the candidates, or at least directly from their campaigns that write this stuff out. So let's go ahead and continue on with the lecture. We're getting towards the end. I think if I hurry, I did waste some time at the very beginning answering. It wasn't wasting time answering a student's question, but I was returning an email for a student. So I think we should be able to finish this up, though. Yesterday, I believe we left off. We talked about transform faults. We talked about the deep sea drilling evidence. And then we got to this, the hotspot in Hawaii, and how the hotspot moves around. And so basically, when they talk about Hawaii, think back to, I'm not going to pull up Google Class or Google, what is it? Google Earth. But remember the plates and how the Pacific Ocean was one giant plate. And so you have Hawaii out here in the very center. That's not near any other continent. It's not near any plate boundary, and yet Hawaii is a volcano. It's volcanic activity. So where is Hawaii getting its melted rock from to fuel those volcanoes? Because we saw with continental plates smashing into oceanic plates, and oceanic plates converging with oceanic plates, the oceanic plate gets subducted, it starts to melt, that melt comes up and fuels their volcanoes, whether they're on land like the Pacific Northwest, or whether they're out in the ocean, kind of like Japan. But Hawaii doesn't have any oceanic plate being subducted. It's literally right in the middle of a plate. And so how does it get its volcanic activity? It gets it from what's called a mantle plume. We also call it a hotspot. We call it a hotspot more often than not. But a mantle plume is essentially a hot piece of the mantle that's rising up, similar to that lava lamp bubble. But there's a couple differences in it. A, it happens over a very, very long period of time. And B, it's independent of anything else, especially the plates. So the plates move on top of it, but the mantle plume kind of stays in the same spot. And so their example here is they have this image. It shows you the mantle plume rising up underneath the hot spot. It shows the plate moving this. No, that's not true. The plate's not moving this way. Yes, it is. I'm sorry. My brain freaked out for a second. The plate is moving this way. So what used to be, if you go backwards, this spot used to be over the mantle plume. And so that's how this volcano got built up and eventually became a volcanic island. But as the plate moves, the mantle plume stays the same. And so this island moves away from the source of the volcanoes, and it starts another island. And that island moves away from the source of volcanoes, and it starts another island. So when you go to the Hawaiian Islands, one thing that you notice as a geologist is they are different aged rocks. So the big island, Hawaii, which still has currently active volcanoes. To be fair, I think all of these kind of have active volcanoes, just the main island is more active. It is a very young island, less than 1 million years old. 0.7 million years to present is the rocks that you're finding on the Hawaiian main island. Then you go to Maui, and everything's a little bit closer to 1 million years old. And then you go to Molokai, and it's 1.3 to 1.8 million years old. Then you go to Oahu, and it's 2.2 to 3.3 million years old. And then you go to Kauai, and it's 3.8 to 5.6 million years old. So they just go from younger to older to older to older. And there is actually an entire chain. So here's Hawaii right at the very tip of this. there's an entire chain of these underwater volcanic islands. These aren't islands anymore because they're not above sea level. They go all the way across the Pacific Ocean and then curve and come up all the way up to Russia and the very tip of that Alaskan island chain. And so what that tells us is that at some point in time, this Pacific plate was actually moving north because the hot spots here, the plate was moving north for quite a while, which created this north-south chain. And then it changed directions and started going northwest. And as it went northwest, it kind of curved and came down this way. The hot spot's been in the same place the entire time, but the plate has constantly been moving, which makes your different islands kind of come along. And this is a very, very long distance for these island chains to happen. And so we have a lot of information and a lot of data on this Hawaiian hotspot. And actually in the lab, you will do a little bit of math work to kind of see how fast that Pacific plate is moving based on the ages of the islands, the distances from them, and you can kind of calculate how fast that plate moved while they were being formed. So let's see. Another thing which I don't mention, another example of a hot spot that's not out in the ocean but is on the continent is the Yellowstone supervolcano. That is actually fueled by a hot spot. Because if you look at where Yellowstone is, they talk about that supervolcano pretty often as far as like clickbait news articles that are like, is Yellowstone about to explode? Is the whole world going to change as we know it? And yeah, one day Yellowstone will erupt again, and it will be a crazy supervolcano event, which will definitely change like the way the United States operates and where people live. It's not going to end all life on Earth or anything like that. It will be an issue. It will be a big hassle. And you know, if people are living directly over it, there could be some loss of life. But I don't know that it's going to be like as bad as some of the news articles make it out to be. Maybe I'm wrong. I don't know. But yeah, the Yellowstone supervolcano is a hot spot similar to the hot spot that Hawaii sits onto. So now we get into the stuff that's really going to be focused on in the lab, which is plate tectonics and magnetics. And the magnetics are very important. And so the idea here is, I don't know that they have a picture. Not really. All right. So the idea here is, as I go back, there are magnetic minerals. And we've already seen some of the magnetic minerals. You saw magnetite in the mineral lab, right? And so when magnetite forms in rocks, yeah, you can have an entire rock that is magnetite. But more often you have little pieces of minerals that are magnetite kind of contained within an overall rock, like let's say a basalt that forms on the ocean floor. And the idea here is that magnetite isn't usually a round piece. Even if it is a round piece, it's going to be a piece of mineral within a larger rock. And these pieces of mineral are going to have their own like magnetic field. They're going to come out of the North Pole. They're going to circle around to the South Pole. They're going to have a magnetic field just like anything else. That magnetic field, just like a compass, you set a compass down, and if you allow it to turn, it's going to turn to align with the Earth's magnetic field. It's going to point north or it's going to point south, depending on the polarity of the magnet. Given enough time to settle within a molten rock, like an igneous rock, so this really only happens in igneous rocks correctly. Given enough time to settle, all of these magnetic particles within a rock are going to point towards, they're going to align with the North and South Pole. They're going to align with the magnetic properties. And so as long as this rock is still overall within a larger piece of rock, and it hasn't been, eroded away, it hasn't tumbled down a mountain or anything, but you actually like drill it out of the ground, or you observe it while it's in place in the rock and you know it hasn't moved. These magnetic pieces can point to where the magnetic pole was when the rock was actually formed. And so there's a lot of work to do this, because you have to remember, when you're talking about continental plates or when you're talking about oceanic plates, they do move. And so you kind of have to think about them moving. But if you do the math and think about it in a all-encompassing way, you can kind of reverse engineer this and figure out exactly where the magnetic pole was when this rock formed. And this actually helps us recreate some of the history of these plates and figure out what was going on at the time. So with this in mind, that you have your magnetic minerals that have poles, and as your rock cools, the grains align in that magnetic field and they get stuck there. Once the rock cools and solidifies, they're locked in place, and they point towards the magnetic poles at the time of formation. What we call that is paleomagnetism. They say fossil magnetism. I've never really heard that because it doesn't have to do with fossils. It's igneous rocks. They're just kind of saying this is like a relic, an old kind of magnetism. So paleomagnetism is more proper. And it shows the position of the paleomagnetic poles and how they appear to change through time because of continental drift. Now, one of the other things we noticed as we went and drilled rocks is the magnetic poles flip. Has anybody ever heard of this? The magnetic poles flipping? Yeah. The magnetic poles actually flip. So at some point in time, actually we think it could be, maybe not within our lifetime, but relatively soon, the North Pole is going to flip at the South Pole. And all our compasses that point north are actually going to point south after that. We'll have to recalibrate all our satellites. We'll have to do all sorts of weird stuff, but it's not going to be like world ending. It's just a magnetic pole flipping. But this apparently happens a lot, and it's happened all throughout history. And as we look at the rocks, we can see this flip happening, particularly at the rocks that are formed in the ocean basins around the mid-Atlantic rift. And so if it's pointing north, and to be fair, this is just us making this up because we've lived during this time. If it's pointing north, we call it the normal polarity. If it flips and goes south, we call it reverse polarity. So just normal and reverse. And that's allowed us to build this magnetic time scale to give about a time frame to how often this happens. So for example, right here, age in millions of years, we start from the present. We are currently in a normal polarity, which is the white one. We had a small flip about maybe 750,000 years ago. It went to reverse for a little while. It flipped back and had a small portion of normal. Then about 1 million years ago, it flipped and went reverse if you're going backwards in time. And so you have a long period of reverse polarity, a short period of normal, a longer period of reverse. Then you go to a long period of normal, and it just flips back and forth all the time. We can see this from pretty active and regular volcanoes. So when the volcano erupts, you have magnetic minerals in them. They align themselves in the lava because they're allowed to freely move inside the liquid. And then when the liquid solidifies, they're all pointing the same direction, which tells us whether it was a normal pole or a reverse pole. So we see it in the volcanic layers that happen over and over again in active volcanoes. But more importantly, we see it in the ocean seafloor. So here's your spreading ridge. It's always creating new land. If you think about like the mid-Atlantic ridge, several 100 million years ago, Pangea was a thing, and then all of a sudden it starts to rip apart, and we start to create this new land consistently in the Atlantic Ocean. So always as it's spreading, you're creating new rock. This new rock comes up with magnetic minerals. They align themselves to the poles. Then as they cool inside the crust, they get locked in place, and we can see that you have these alternating bands. In the white stuff, it's pointing north, and the pink stuff, it's pointing south. And we can actually see this in the rock record. They have technology that they use in boats, survey boats that kind of read these magnetic fields as they pull across the bottom of the ocean surface. And we can get really in-depth, detailed maps. So this is obviously idealized a little bit. This is kind of more of a true map that you would see as you're doing this. So this is off the coast of the northern part of the United States. Here's Canada up here. Here's the Juan de Fuca Ridge. So this is probably like Vancouver Island, I think. And you're talking about Washington State and the Olympic Peninsula up here. And then off the coast, you have these readings, and you can see the linear lines of the normal polarity in white and the reverse polarity in red. And so once we started to notice this, we knew that this was a great indicator of the poles flipping back and forth, how often they did it, what the dynamics were, and kind of that led us to understand a little bit more about our magnetic poles and the dynamics there. So here is a progression to kind of show you. It starts off with reverse polarity. Here it's doing normal polarity. As it continues to spread, it flips, then it flips again. And not only do you get these stripes, the stripes on the left side match the stripes on the right side. And so it's kind of a mirror image of each other. White, and then red, and then a little white, and then a little red at the end. And so because it's both being created equally on both sides, you kind of have that mirror image. So what does the evidence support the plate tectonic theory? The age and thickness of the seafloor sediments, and we saw that, how it's very thin and very young towards the center of the mid-ocean ridge, and thicker and older towards the end near the continents, further away from the mid-ocean ridge. Hotspot tracks like Hawaii show the movement of plates over time compared to your stationary hotspot. And then apparent polar wonder, which, let's see real quick. I want to show you all this. There'll probably be another SCOTES video, like I showed you yesterday. But that's what SCOTES really work on, is the polar wonder. Apparent polar wander, like you're wandering through a forest. Videos. I don't want to see how. I want to see it actually move. Oh, this is weird. Why is your head like detached like that? And it's literally just a video of your face. That's false advertising. Anyways, I thought I was going to get a better video than this. Yeah, here we go. So this is at least just going to show you. So this is the pole moving around. And sometimes it doesn't really move in straight lines like you might think. It's a very dynamic thing, because it's basically based on the iron and the nickel flowing through the core and the mantle. And so that creates your magnetic field. So it moves around a lot. We can trace this back fairly accurately, hundreds of millions of years into the past using the rock record and the magnetics. I think this is just the same thing repeating over and over again. But that polar wonder actually helps us pinpoint where the continents were. Because we can see that the continents moved together like in Pangea, but where on the globe was Pangea? Was it right along the equator? Was it down near the South Pole? Was it up near the North Pole? And so we use the magnetics to help us understand not just how they moved related to one another, but how they moved related to the poles. Were they in warm climates? Were they in cold climates? And we can kind of match that with the rock record that we have. So polar wonder is actually pretty cool. I don't want to spend a lot of time on it, but I wish I had a better video. Maybe I'll find another one. So, they're totally going to take my video down. I got to remember that. I can't show YouTube videos on my videos. So magnetic reversals and seafloor spreading are going to be the last thing. And we will do, in your lab, you will do work on hotspots, and you'll do work on the magnetic reversals and the seafloor spreading. And I will get that put onto Canvas probably tonight. I need to do tests and labs on Canvas. So what drives, this is part of why the continental drift hypothesis didn't stick around, and we ended up going to plate tectonics, because they never really answered the question, what actually makes the plates move? Why do they move the way they do? What is forcing them to do that, and why do they change sometimes? So we have two different things. These two are actually one. These are flip sides of the same coin. So you have slab pull and ridge push, and basically this is gravity. Gravity is going to cause your plates to kind of move once they get started. So see how this is being subducted. Once it starts to go down, gravity is going to pull it down even further. And so it's almost like a a rope like falling off a table or something. Once you get enough of it on the side, gravity's going to pull it down. And it's just going to keep like pulling itself off. And so the slab is pulling down this way, and at the ridges, it's not much, but it's enough. Because they're elevated, they get pushed up by your plume that's coming up and filling in these cracks. Because they're elevated, gravity is going to be trying to pull them down and even them out with the surrounding plates. And so as gravity pulls down, they don't have anywhere to go but outward. And so they're kind of being pushed out by gravity. And so you have this ridge push, which is happening, and you have the slab pull, which is pulling it down below. And that's going to keep this plate moving this way and that plate moving that way, because you should have them on both sides. The other part of that is going to be your convection currents. And just like any convection, like in a coffee cup in the earth, we have, and we argue there's not a consensus on exactly how this works, because some people think it's really simple, some think it's really complex. It's probably more complex than simple. But essentially, you have your really hot core, and then you have your really cold, solid crust around the outside. Hot things are going to rise, cool things are going to sink, right? So as it gets heated up by the core, parts of the mantle will rise up because they've been heated, they expand, they're a little bit less dense than surrounding stuff. So they're going to rise up. Everything that rises up has to be replaced by something else that's coming down. So the cool stuff from the top that's gotten near the crust but hasn't like solidified as the crust is going to start to come down to fill in that spot. And what's most important is at the top, you're going to have like this replacement. So whichever way your convection cycle is going, that's going to help to push that continent or that oceanic crust in that direction as your convection cycle actually happens. And so we see that you have these kind of dynamics within the mantle that are causing that pushing. And they even kind of show that here. As your mantle material comes up to fill this crack, it's going to come out, and both of these kind of also help push along that plate and keep it separated. So it's those two things. It's convection and it's ridge push and slab pull, which are kind of the same thing that just happen in different areas. So they talk about mantle convection flow drives plate motion. From what we understand, you kind of have to say that mantle convection is the primary force because it's got to start everything first. It's not until you've already started the movement that your ridge push and your slab pull can actually come into effect because of gravity. So the mantle convection is thought to be the primary thing that's moving it. Once they start to subduct, then gravity can take over and you can get your slab pull and your ridge push. Let's see. I think they'll show a second of the different models. So like I said, you have a simple model which shows whole mantle convection and big circular currents of convection. And then you have a more complicated model, which I guess some people call the layer cake model. I don't know that I've heard of that, called that a lot. But here is your big circular one. No. Well, these are both a little bit more complicated. But anyways, you can see that there's an argument, and we don't really have the tools to see exactly what's going on just yet. And so both of these are kind of used interchangeably depending on what you're talking about. But this one would be the whole mantle convection. You can see the big convection circles going all the way from basically the core, coming up, and going all the way back down to the core after they cool up at the surface and come back down. And as that circle happens, you get directional motion on the plates in different areas of the world in different directions, which kind of makes sense because we've got plates kind of moving all over the place. Here would be the layer cake model, and it shows your convection happening really just at the surface. I've seen other models that have this, but also have a lot more complexity down below that instead of just a simple, like, big layer down here at the bottom. So we're still trying to figure that out, but we do know that the convection is one of the main drivers. We just have a hard time visualizing or getting evidence of exactly how that convection works. And so maybe one day we'll get some better technology and be able to do that. So what is meant by plate mantle convection? Basically, your cool, dense oceanic lithosphere sinks, your warm mantle upwells at the mid-ocean ridges, and at your mantle plumes. And what is the primary driving forces of plate tectonics or plate motion? They're going to say slab pull and ridge push once it gets started. It's pulling on it because of gravity and pushing it down the hill also because of gravity. So how do plates and plate boundaries change? Like I said before, the Earth's not getting bigger. You have a total surface area that's always going to stay the same. And so anything that gets destroyed in a convergent boundary has to be replaced by creation at a divergent boundary. The size and shape of individual plates do change. Africa and Antarctica plates are growing because they have spreading centers on the sides, and so they're just going to get bigger. They're surrounded by divergent boundaries. The Pacific plate is being consumed, and so it's getting smaller and smaller because it has convergent boundaries pretty much everywhere. And so the Pacific plate will eventually, unless things reverse and change direction, which happens, the Pacific plate will eventually be gone in the future, which may lead to another supercontinent like Pangaea. Imagine that. Political stuff is complicated enough right now. We're all separated and have oceans between us. Imagine if we all lived on the same piece of land, and all the boundaries would be weird because you wouldn't have like the same like land masses or shapes. It would all be scrunched together. We'd be fighting over mountain ranges. It'd be weird. So plate boundaries move and change throughout time, and that's always going to happen. They show you what is this? Here's Pangaea, and then you start to see Pangaea break apart. The upper part kind of separates from the lower part first, and then they all kind of separate towards their present day locations. But that's going to keep going. The Atlantic Ocean is going to get bigger. Everything's going to kind of move around to the other side of the planet. So pleasant plate motions can be used to predict future positions. And so what do they have here? That's not a future position. This is back towards Pangaea. I don't know what they're trying to say here. I guess this would be older, this would be younger, and then if you keep going, we would kind of spread around, but they didn't get to that point. So, that's the end of the PowerPoint. I will try to get the lab up. Probably what I'm going to do is in Canvas just set up answering spots, and I will actually print off the paper lab for you. And you will just go into Canvas and put in the answers as you do the paper lab. That way you actually have something to write on and do things with. It takes a little bit of measuring and physical distances and stuff. So we'll probably do it that way. That'll be easier than actually putting all the images into Canvas. Expect that this week sometime. What is today? Wednesday? If I can get it in, which I should, my wife works late today, so I should be working on that stuff while she's still at work. Then we'll talk about that tomorrow and maybe work on it in class a little bit, and then possibly start the next chapter Friday. No, Friday's the test. Friday's going to be the chapter 3 and 4 test. So make sure you're done with your chapter 3 and 4 homework, and kind of use that to study for the 3 and 4 tests. Nice. So if you have any questions or anything, let me know. If you're online and you have questions, please email me. And everybody have a nice day.